advisors for Brian, along with Dr. Tim Hagan. Just want to welcome you to his defense. I'll give you just the overview of the process, and then Dr. Hagan's going to introduce Brian. So Brian will give a 50-minute presentation on his talk, after which there'll be a Q&A session for the general public. After that point, he'll meet with his committee, besides Dr. Hagan and myself from the Department of Chemistry and Biochemistry of Dr. Gaillard, Dr. Baker, who are serving on the committee, Dr. Staffstrom from the Department of Biological Sciences. We also are expecting Dean's designee Dr. Chakrabarty from physics. Hopefully he'll come in a second or so. But that will be the overview of the process. Oh, there he is. Good time. Welcome.
So I am Tim Hagan, one of Brian's co-advisors. So I'll just give a brief summary of Brian's educational background and a few other items. So Brian earned his associate's degree at the College of DuPage. Then he earned his bachelor's degree here at Northern Illinois University in 2011. And he's been a graduate student in our department here since January 2012. Brian's been a teaching assistantship here at NIU, doing a very good job with the biochemistry lab primarily. He's also mentored undergraduate students. He did receive the Kevin Cull Memorial Teaching Award, which is outstanding teaching abilities. Brian does have industrial experience. He worked at VBF, which stands for Vegetable, Vitamin, and Food Company. It's actually was established in India, and they've got branches all around the world. And he did quality control, primarily working with glycerin and other natural products which were used in soaps and detergents. He's got several posters that he's presented at regional and national meetings, and he's currently working on 3 different manuscripts from his PhD work, which he will tell you about shortly.
Thank you very much. Welcome, everybody. My name is Brian Hartnett. Some of you might not recognize me without a superhero shirt on and a hat, but I assure you it's me. Today I'm going to be talking to you about the work that I've been doing with characterization and inhibitor evaluation of ISPD and ISPD enzymes from the non-mevalonic pathway. Now, an overall goal of what we're working on. The overall objective is characterizing enzymes. We're going to be characterizing ISPD and ISPE enzymes. And we're going to use these enzymes with it to assay compounds. We'll have a library of compounds, and to assay these to see if we can get any potential hit compounds that will bind to these enzymes. These potential hits can then be further evolved into lead compounds, which hopefully can eventually become new antibiotics. Now, why do we need new antibiotics? There's plenty of antibiotics on the market, right? Antibiotic resistance right now, whether you know or not, is one of the hugest threats to human health right now. And it's rising at an alarming rate. In 2013, the CDC says there's approximately 2 million illnesses due to antibiotic resistance and 23,000 deaths. As you can see from the table, as I stated, it is rising at an alarming rate. The way that antibiotic resistance comes about is bacteria, the cells split. As the cells continue to split, there's inherent mutations that happen. It only takes one cell to have a mutation that could cause resistance to antibiotic. As this bacteria is treated with that antibiotic, it starts to kill off the cells that don't have a resistance to the antibiotic, which continue to multiply. And subsequent treatments of this antibiotic could leave a strain that's completely antibiotic resistant. Now, what else is alarming, besides this increase in antibiotic resistance, is the decline in antibiotic development. Now, this can be due to several reasons. Within the last 30 years, there's been a sharp decline in antibiotic development from large pharmaceutical companies. One of the reasons is antibiotics are less profitable. Probably one of the main reasons. It takes a lot of money to recoup costs of developing a new drug. Antibiotics, usually you take, your Z-Pack or whatever, and it kills off the it kills out the bacteria infection. So a lot of pharmaceuticals focus on drugs that you take on a daily basis, such as statins or ACE inhibitors. Another reason is higher drug regulatory standards for all drugs keeps increasing over the years, so it costs more to develop these drugs. Again, so it comes down to the money with that one. So, how are we fighting back? Well, the world is fighting back in the United States and in 2012 they passed the GAIN Act. The GAIN Act focuses on drugs after they've been developed. So they extend the exclusivity period by 5 years. Now what does that mean? That means you get more on your patent for the most part. When you patent a drug, the patent is 20 years from when you actually set the patent out. It's not when the drug hits the market. And unfortunately, for many large pharmaceutical companies, it can take 8 years to bring a drug to market after it's been patented. So adding another 5 years adds another 5 years for them to recoup their costs. It also fast tracks the FDA review. Europe also is helping out, but they're focusing more on the preclinical trial portion of drug development. So they create and manage drug discovery platform. They're focusing on creating the drugs before they get to the clinical trials. So what are we going to target? We need a new way of targeting antibiotic resistance. So we're going to focus on targeting isoprenoid development. Isoprenoids are one of the largest classes of compounds, and they're imperative for life. Isoprenoids are base compounds that create cholesterol, they create ubiquinone, create chlorophyll in plants, and there's two pathways that create these precursors that make isoprenoids. First is the mevalonate-dependent pathway. Now, mevalonate-dependent pathway is found in some bacteria and the cytosol of higher plants, but also in eukaryotes, especially humans. Conversely, the MET pathway, methyl erythritol phosphate pathway, is found in some bacteria, the chloroplasts of higher plants, and most importantly, not humans. So focusing on the MET pathway will allow us to not have much crossover, won't have any, less likely to have side effects or hitting off targets. A couple of known inhibitors of these pathways, if any of you are taking statins, this targets the mevalonate pathway, and phosphamidomycin is a target for the non-mevalonate pathway. So let's take a little closer look at the MET pathway. The MET pathway, as I stated, its precursor makes the precursor IPP and DMAP, which dimethyl allyl pyrophosphate and isopentyl pyrophosphate. I will be looking specifically at ISBD and ISBE, which is the third and fourth enzymes in the pathway. ISBD is a transferase. It converts the MET substrate to CDPME, which subsequently catalyzed by ISBE to the CDP-MEP substrate. So, well, there's thousands of pathogens we could look at that are developing, but we want to focus our work on this to two specific pathogens. One is E. coli. Most E. coli is harmless. It's everywhere. You have it in your gut. However, the harmful strains, they can be transferred by water, food, contact with infected animals or humans. And it is a nice model system to work with. There's a lot of information about E. coli. Now, Burkholderia talondensis, the reason why we're looking at Burkholderia talondensis, we're using it as a model system for Burkholderia pseudomeli. Burkholderia pseudomeli is a tier 1 select agent, which means it can be used in bioterrorism. The select agents are agents that could, and since it's tier 1, it is thought to have the most amount of casualties. Just Burkholderia pseudomeli right now has about 89,000 deaths per year. Now we're not just going to randomly throw a bunch of compounds at these pathogens to see if we can stop them from being active. We want to go a more knowledgeable approach to this. We want to have some sort of method to our madness. There's 2 routes that we've taken for this. The first one is basically a knowledge-based approach. Oops. Knowledge-based approach is using known inhibitors, known substrates, and basing our compounds off those. Known inhibitors in the literature of ISPD and ISPE. ISPD has the L-erythritol phosphate and phosphatomycin for E. coli. Now they have very weak potency, the strongest being 1.36 millimolar, but they are in the active site. They do mimic the substrate. 2 more inhibitors that we know of the ISPD enzyme have very good potency in the nanomolar range. However, they are allosteric inhibitors, which means they do not bind in the active site. And they do not have activity against E. coli. ISPE, we have stronger inhibitors in the low micromolar range, 2 that mimic the substrate, and 2 others from the literature found in screenings, library screenings we'll talk about in a moment. That is the other course that we are taking besides the knowledge-based approach, is screening libraries. Libraries are large, is a large library of compounds. We used, not here, but there was a fragment screening done by STD-MR, which is saturation transfer difference NMR, against ISPD, E, and F for Mycobacterium paratuberculosis, Mycobacterium abscessus, and Burkholderia pseudomeli. And with this, we found 37 fragments that bound to both ISPD and ISPE. 2 of these fragments being FOL 7185, which is a pyrazole pyrimidine, and FOL 7082, which is an oxidiazole. These fragments were used to make analogs to see if we can increase the potency of these compounds. There we go. So my goals in this research. First goal is to do biochemical analysis of the ISPD enzyme and evaluation of inhibitors against the ISPD enzyme. Second goal is discovery of small molecule inhibitors of E. coli ISPD using a library-based screening. And our third goal is similar to goal 1, except for I'll be doing biochemical characterization and evaluating inhibitors of ISPE. So first goal, biochemical and structural characterization of ISPD. ISPD, as I stated, is the 3rd enzyme in the MET pathway. It is a transferase, which means it acetylates the phosphorus, the phosphate, on the MET substrate. In this active site, there is magnesium. There's a magnesium cofactor metal. However, this magnesium has is not important for the folding the actual protein. What it's there for is to coordinate the substrate in the active site. So looking at the structure, more of the structure of ISPD, the weights of both E. coli and Burkholderia thalamodensis is about the same. ISPD has a long beta arm, which coordinates with the other monomer, forming a dimer, and the active site is at the interface of these dimers. Now, this active site is known to be a difficult active site to target. It is the least lipophilic active site in the MET pathway. is also highly solvent exposed, which is why it's difficult to target. Just to put it in that perspective, AstraZeneca in 2015 performed a library-based screening against E. coli ISPD against their library, which is 1.7 million fragments. They did an enzymatic assay with higher constraints, but they found no hits. So this is definitely a difficult site to target. So looking at the sequence similarity between the two, of E. coli and Burkholderia thailandensis, there is a 39% sequence homology, which doesn't sound like a lot, but it does fold similarly. Most importantly, there's a 91% active site homology, which means that we could probably, there's a good chance that an inhibitor of one could inhibit the other. The difference being there's an alanine in the Burkholderia thailandensis. So, okay, so we characterized structurally and in the sequence of the two enzymes, need some enzymes to work with. So this posed the next problem to work with, is purifying them. Purifying these enzymes, we had the parent vector encoded with our gene, and this parent vector did add an antibiotic resistance along with a histidine tag, a 6-histidine tag. It was then transformed into BL21DE3 strain of E. coli. It was grown up in a culture of lysogeny broth and induced with 1 millimolar IPTG. After the cells were grown overnight, they were lysed open using sonication, and after they were lysed open, we purified using a nickel affinity column, which coordinates with the 6-histidine tag that was incorporated in the parent vector. Further purification was done then with size exclusion column with a Superdex 75. Was able to get a yield of 45 milligrams per liter for E. coli ISPD and 10 milligrams per liter with Burkholderia thailandensis ISPD. So now that we purified it, we have our purified proteins. The next step was to determine the thermal stability of these proteins. Now, thermal stability is when proteins are in their native state, they're folded up. As you increase the temperature, proteins end up unfolding and losing their secondary structure, leaving us, and we're able to follow this unfolding to give us a thermal stability profile. Adding some sort of ligand could stabilize this protein if it binds to the active site. So we could use this for further studies. So we can look at this thermal stability. This thermal stability was looked at directly using circular dichroism. Circular dichroism looks at is a direct analysis of protein, and it gives an overall global profile of the secondary structure of the protein. We can follow a wavelength as we increase the temperature, and the wavelength in the profile showing us of the secondary structure. We can follow the wavelength as we increase the temperature. As we increase the temperature, as I said, it starts to unfold and lose its secondary structure before it starts losing the signal, and will give us a thermal shape profile, a thermal stability profile. We're able to determine this 50% mark where half of it's unfolded, half of it's folded. Now, this is a really important point. We call it the melting temperature. Now, studying this indirectly. The reason why we want to study this indirectly is because this is a great technique to use. However, it takes about 4 hours to run one sample. Now, if we want to run it against a library of compounds, we're going to need something a little more high throughput, something where we can run more compounds at a time. So I use differential scanning fluorimetry. Differential scanning fluorimetry, as I stated, is an indirect approach to studying the thermal stability of a protein. The reason why this is an indirect approach is because we have the protein, we add in a dye. This dye recognizes hydrophobic residues, which are on the inside of the protein. as the protein is heated and it starts to unfold, these hydrophobic residues are exposed. The dye recognizes the hydrophobic residues, and we get an increase of fluorescence. Now, we can use this as to observe binding with different compounds. In its native form, if we add a ligand in and we have binding in its native form, we're going to pull the equilibrium to favor the native form because it's more stable, and we get a positive shift in our temperature. The reason why we have a positive shift is because it stabilizes, takes more energy for it to unfold, which means more heat. Now, conversely, really quickly, is we could get a compound to favor the unfolded form, which would pull it to the left, shift it to the left, destabilizing the protein. Okay? So, looking at the thermal stability of my proteins, determine with DSF and CD to get a baseline in order to perform further experiments with the compounds. For E. coli and for for E. coli, for DSF and CD, we get roughly around the same melting temperature. We'll also perform for both Burkholderia talondensis, same. We got roughly the same melting temperature. And they're also within a modest range of a temperature scale, so it's where we could use these for our thermal shift assays if we can see a shift either way. It's not, we don't have a melting temperature of 80, 90 degrees where we wouldn't be able to observe the thermal shift. So performing this thermal shift on the oxidiazole series, which was developed off that fragment hit as I described earlier, we did not observe a significant shift. And by significant, I mean we did not even observe anything over 1 degree change. Now, this could be due to it was done on E. coli ISBD, and as you know, as I showed before, these assays were performed on a different species. Those were done on Burkholderia pseudomeli. It could also be due to too low of a concentration used. So for goal 1, I was able to successfully optimize the expression for both E. coli and Burkholderia talondensis, giving us enough protein to work with. There's also, they have modest melting temperatures, so it is within a range that we can work with for thermal shift assays. Oxidizole series at this moment did not show any significant thermal shift. They could be studied further. So on to goal 2. Goal 2 is using this thermal shift assay that described in the previous goal against the library of compounds that are not based off, this was not from a knowledge-based approach. We did those fragments that we used, that we know those inhibitors, that we know that they were binding, so we developed compounds based off that. This is off a large library of 2,500 different compounds. Now 60% of these are drug clinical candidates, 25% are natural products, and 15% are other bioactive components. So a relatively large compound, a relatively large library. This was done at Northwestern University. Now, results from this, we found, against the E. coli ISBD, we found 48 compounds with some sort of change in the thermal stability. Now, this ranged everything from negative 13.53 degrees Celsius change to a positive 3.53 degrees Celsius. Positive 3.53 being thimerosal. Negative 3.53 was cadmium acetate. We picked 2 compounds that we wanted to evaluate a little bit further to see if we could replicate the thermal shift with this. Top picks for further observation was thimerosal, which had the highest shift of 3.53, and zinc pyrithione, which is negative 7.72. Now you might ask why I didn't pick the negative 13.53. Well, this was based on the profiles, the thermal unfolding profiles. We picked the cleanest looking ones. So thimerosal, many of you know This thimerosal was used as an antibacterial in vaccines, or antifungal, antibacterial in vaccines. They're taken out of most vaccines now. But we wanted to see which portion of this molecule is causing the thermal shift. So we dissected this thimerosal into two parts, the thiosalicylic acid and the ethyl mercuric chloride. Performing the thermal shift assay on both portions of this, the thiosalicylic acid had negligible change on the shift of the E. coli ISBD, while the ethyl mercuric chloride portion had a positive 4-degree shift. So we can conclude that the ethyl mercuric chloride is most likely the driving force to the stability of this protein. Okay. So now we have the thermal shift. We know that it's affecting the stability somehow. We have an idea of binding. Now, thermal stability, while it's a good assay for it's a quick initial screening, if we know it's binding, but we don't know where it's binding or how it's binding, so we need a way of, and binding also doesn't equate activity. So we wanted a way to evaluate the activity of these compounds. So I developed an assay, an ISBD assay, which follows one of the products from the conversion of MEP to the CDPME. When MEP is converted to CDPME, it utilizes CTP, which gives off a pyrophosphate. Sorry. This is broken down into an organic phosphate, which reacts with the MESG substrate and reacts with purine nucleoside phosphorylase. And this causes a shift in the maximum signal of 330 nanometers to 360 nanometers, which we're able to observe on a plate reader. Phosphamidomycin, we have a reported value of 20 millimolar. We use this as a control to see if our assay was working, and I got a IC50 at 13 millimolar. So using this enzymatic assay against the thimerosal portions, we saw that ethyl mercuric chloride had an IC50 of 133 micromolar, which is significantly better than the 20 millimolar that we know from the literature. However, looking at it against the phosphate standard, which is just the reaction mixture of the MESG and the purine nucleoside phosphorylase along with ATP, is we got a reduction in signal from the ethyl mercuric chloride as opposed to the thimerosal and the phosphate standard, which we concluded to be the ethyl mercuric chloride reacting with the secondary enzyme in the assay. For the activity of the spectrum collection hits, we did go back to Northwestern University. I did perform the activity assay against all 48 of the compounds. I got the 3 hits for the activities. We have thimerosal, which, as I stated before, it was found in vaccines and it's got antimicrobial properties. Isoleucotenogen, which is a chalcone, and it's actually from licorice. It's currently being studied for cancer treatment along with cocaine addiction. And also carnosic acid, which is from rosemary, and it's found in many chewing gums and toothpaste. Also has antimicrobial activity as well. So we have a range of, in the high micromolar range, but still a significant difference from the recorded values of the reported inhibitors for E. coli ISBD. So conclusion for goal 2, the initial screen, we got 48 different compounds. 48 different compounds from out of these 2,500 compound library with either positive or negative shifts. With these 48 compounds, they were evaluated further with an enzymatic acid, and we did find several compounds with modest activity, which would be more than what the reported values in the literature are. So for goal 3 is evaluation of ISPE. ISPE, the fourth enzyme, converts CDPME to CDPMEP. And it's a kinase. And it also has a metal cofactor for coordinating the substrate. Looking at it structurally, most literature references refer to it as a dimer, and it has an active site of 2 pockets that are right next to one another. We have an ATP pocket and a CDPME pocket, one for each of the substrates. And again, they are in the interface of the dimer. So the sequence similarity between the two: 43% overall homology between Burkholderia thaladensis and E. coli, and an 87% active site homology. The CDPME site is actually 100% sequence homology. And then with the Burkholderia thaladensis, there are 2 aspartates which replace the asparagin's in the ATP pocket. So again, we have the structural and the sequence of these enzymes. We need something to work with. So this, again, with the challenge of expression, the same procedure for expression. However, E. coli did not express very well at 2 milligrams per liter. And Burkholderia thaladensis did better with 28 milligrams per liter. E. coli, we have to look at a little bit more how to improve the expression with this, along with the activity of the 2 milligrams per liter is not fully active as well. So that needs to be further evaluated too. So again, we need to look at the thermal stability of these as well. So I looked at the thermal stability for DSF and CD for both these proteins. For the E. coli, we got comparable thermal shift, and also within a range that we could work with for thermal shift assays. And Burkholderia thaladensis, again, we have comparable and in a modest range to use for our thermal shift assays as well. So back to the fragments. Again, these 2 fragments, since we know bind from the screening bind to ISPD and ISPE, these series of oxidiozoles and pyrazolopyrimidines were evaluated further for ISPE now. With the thermal shift assay, the pyrazolopyrimidines did not show too much of a significant shift. We did get 377, which had a 4-degree shift. That is the pyrazolopyrimidine, but it had a furan ring instead. However, we have a more significant range with the oxidizole series. When we look at these even further, we want to, again, we have an idea what binding, we want to know activity, right? So developing an assay so we are able to study the activity of these ISPE enzymes. Now this plate-based assay is actually following the luminescence and not fluorescence this time. And it also follows a reactant. This kind of makes things a little counterintuitive when you're reading the results, because it follows the ATP, which interacts with beta-luciferin, and it does give off a luminescence. So the higher the signal is, the less active. Like I said, it's kind of counterintuitive. So the lower signal is the more active. So we have some compounds that we have from literature, and NIU and an NIU inhibitor that was evaluated at the University of Hamburg. Hagen 779 and 813, both these compounds are from literature, and found to have 17 and 19 micromolar range. These were found using the kinase glow assay as well. And these were from a library screening. And Hagen 333, University of Hamburg evaluated this with an assay that was like a compound assay to find to have an IC50 of 7 micromolar. So we can use these as standards to see if how our kinase glow assay is working. So looking at these compounds further, ISBD beat Burkholderia thailandensis, had a micromolar rate, IC50 of 169 micromolar, while E. coli had micromolar 31 micromolar IC50, compared to the 7 micromolar from the literature. 813 is 140 micromolar and 34 micromolar for Burkholderia thailandensis and E. coli respectively, compared to the 19 micromolar in the literature. I should also make the note that these IC50s from the literature are against E. coli. And our oxidiazyl Hagen 333 compound, which is the dichlorobenzene compound, we found to be the most potent with 28 micromolar against Burkholderia thailandensis and 3 micromolar against E. coli. So it was the most potent against both enzymes that were studied. Now, looking at all of the compounds that were screened. We did screen pyrazolopyrimidine and oxidiazyl compounds. I know these are a lot of numbers, and just what I want you to take from this is that there were not many compounds with enzymatic activity against the pyrazolopyrimidines, and the ones that do have activity are in the mid to high micromolar range. However, the oxidiazyl had a much larger range of activity, from 3 micromolar all the way to 900 micromolar. Again, another thing that I want to take from this as well is comparison of the thermal shift assay to the activity. We did not observe any correlation between something having a thermal shift and the activity. As you can see with this, between thermal shift and IC50, it would be really nice that if we saw 1 degree shift, we would see activity in 500 micromolar range. Okay, we see a 2 degree shift, we'd see activity in a 250 micromolar range. We did not see that any type of correlation between the two. But our activity that we did have a structure-activity relationship with this oxidiazyl series, which was really nice to see. As we continued to add substituents to our oxidiazyl fragment hit, we can't see an increase in activity, except for 826, which there could have been several reasons why there was no activity with that one. One being that the concentration could have been wrong. It could have also precipitated out of solution as well. However, as changes were made, we can observe changes in the activity as well. So say looking at 840, we have a benzothiazole. If we made the change to just indole, we could see a loss of activity. Now, conversely, if we look at Hagen 333, which was our strongest compound, again, if the same change was made, we get a loss of activity, which signifies that it is important to have the benzothiazole as a substituent on this oxidiazole. You can also see, as we made a change from oxygen to methylene, there's not a significant drop in activity. So we can conclude that this oxygen probably is not significant for binding. So, as I stated, Hagen 333 is our strongest compound that we've observed so far with this assay. So looking at this a little bit further, we did perform an ITC with this, which is isothermal titration calorimetry. With the conditions, it was pH 7.4 at 25 degrees Celsius and 10% DMSO. And any of you who have done ITC are probably cringing at that 10% DMSO. However, I was severely limited by the solubility of this compound. So we did determine to have a KD value of about 455 nanomolar, a delta G at 8.6 kilocalories per mole. And we have stoichiometry of 0.9, so around 1, so that one Hagen 333 binds with one monomer of ISPE. So we do know that this is an entropically driven compound, or compound with binding to the ISPE. So these binding studies give us a little more insight of how they're binding. So, in conclusion to this, overall, we did show low to moderate melting temperatures for these enzymes, so we were able to use a thermal shift assay. Sequence homology is similar, so we could suggest similar activity. And also the IC50 values that were determined were in the low to mid micromolar range with the oxidizole series. So that's very promising for us for future development. Hagen 333 identified antibacterial activity with KD value around 400 or around 500 nanomolars for Burkholderia thalidomyces ISPE. So overall, structural and characterization of ISPD and evaluation of inhibitors. We did determine melting temperatures and the stability of E. coli and Burkholderia thalidomyces. And observed that these were in fact able to be used for thermal shift assays. Goal 2 is we use these thermal shift assays with a large library of compounds, the microsource spectrum collection, and out of that we were able to find 3 compounds in the high micromolar range of activity. And then goal 3, we looked at the structural activity and evaluated inhibitors for ISPE. We found melting temperatures and melting stability in a range that we can utilize for thermal shift assays, along with performing enzymatic activity and finding very promising results with some of our compounds. And with that, I'd like to thank you. I'd like to thank the NIU Department of Chemistry and Biochemistry. I'd like to thank my committee members, Dr. Horn, Dr. Hagen, Dr. Stastrom, Dr. Baker, Dr. Guyard. Appreciate it all. I'd also like to thank Dr. Chiao Luan that I worked with at Northwestern University with the Spectrum Collection. Dr. Darren Begley from Beryllium, who performed the STD-NMR experiments, NIU Venture Grant, Horn Lab, Hagen Lab, family. Deanne helped out a lot. So thank all of you. And the deans, I think Dr. Vardy. So with that, I'll take any questions.
You look very dapper, by the way. I love the suit. I just need a little clarification on the compounds you started with. So you said that there were some already, they were weakly binding, but you said another problem was that they were allosteric binders. Is that because the sequence homology is more similar between the active sites, you want to target that, or are you looking at anything that affects the activity? So why allosteric versus binding in the active site?
Okay, so I was talking about the known inhibitors.
Mm-hmm.
So the 2 known inhibitors that we had were both, they're known to be the allosteric inhibitors. We were just targeting, we don't know exactly which site we're targeting at the moment. We just know that off the fragment hits based off STD-NMR, that's why we were targeting the active site.
Okay.
So what's next for the Hagen 333? Like, you've done a couple of different things that is to correlate what you're seeing is obviously going to be inhibiting, but what'll be next for that compound?
Ideally with that compound would be glorious to get a crystal structure. That would be wonderful. Also would like to reperform some ITC experiments, try cleaning that up as well. But
10%
crystal
TMS
structure
sounds
would be
hard.
glorious for that.
Okay.
10%.
Yeah,
Yeah.
exactly. Like it's
That's
it is highly
sad.
Yeah.
This is sad.
Yeah.
On slide 42.
Even some numbers.
Maybe 41. That one, yeah. Did you introduce that compound enantiomerically pure? Or did one show activity more so than the other?
I'm honestly not sure.
Fair enough.
I did not look into that. It's just a compound that we purchased.
Okay.
It was for Shannon.
Was it?
Other questions from the non-committee members?
Have you published or planning to publish this?
We have three publications that we want to work with. One of them being with the spectrum collection work. That would be ideal, looking at with those results from the spectrum collection, and also with both the oxidizole and pyrazole pyrimidine series for the ISPE work, the enzymatic work and the mission.
And what are the future plans for you? Go from here?
Future plans from here? Job for.
You can live here forever with me.
No.
Thank you.
No.
I really want industry.
Yeah.
I like the pharmaceutical work, but I also like I also like I like enzymatic work in general. So.
Well, that's your future. I was talking more about.
Oh. Isn't your future?
No, that's fine.
If you want to know more, no. For future work for the Hagen 333 or just the work in general. We have a couple of other series of compounds that we want to look at with a few more oxidizole series compounds that we want to evaluate further with the enzymatic assay. So there's actually quite a few more compounds in our library that I need to work with more. But as I was stating before, crystallization would be great, but I don't know if I'll have time to get to crystallization. But
And just out of curiosity, and pardon my ignorance, at some point does this go into are these tested on lab animals or?
that's kind of out of our range in an academic standpoint. I don't think that would be in a range that we could actually do here.
No, I was not.
Yeah,
That's why I said it's
yeah.
out of curiosity. Is this knowledge handed over to some other lab that eventually, if this is someday to be applied on humans, what are the steps from what you have done to it actually being used on humans?
Well, for one, we need to get something way more potent than what we're at right now. 3 micromolar is not a range that they'll be significantly looking at for any type of. So further analogs development of, if we go further with, say, Hagen 333, is further analogs of that to get it more potent in it before anybody would significantly look at it or consider taking over the project.
Thank you.
Yeah.
Any other questions from the general audience? Okay, so if not, at this point, we'll move over to the committee, but let's thank Brian one more time.